This Zoom session is being brought to you by the Fractal Crystal Ball. All right. For today, section 1.4, properties of functions. Even or odd, increasing or decreasing, symmetries, and let's see what else is there, and extreme values. So we proceed. Let's start with the graph of the equation y equals x squared. It's this U-shaped parabola graph. It's the same shape as the curve of the cable on the Golden Gate Bridge. It's also the curve of an object falling at free fall. And that's also what they use for the back of a for the shape for the mirror of a radio dish or a flashlight, because it focuses lights. Anyhow, so if there's a point x by x squared on the graph, the negative x by x squared is also on the graph. So these two are symmetrical through the left to right. It's symmetrical through the y-axis. Now here we have x equals y squared is the same graph on its side, and it's symmetrical up or down. Flip y to minus y, x stays the same. And then here's a graph of x squared plus y squared equals 1, the circle. And if x by y is on the graph, then negative x by negative y is also on the graph. So this one is symmetric via reflection through the y-axis. This is symmetrical by reflection through the x-axis, and this is symmetric by 180-degree rotation through the origin, around the origin. Now this is related to what's called even and odd functions. An odd function is one where f of negative x equals negative f of x. I say that it transmits the negative. So for example, x to the third power, x to the fifth power, x to the seventh power, those are all odd functions. Indeed, x to an odd power is an odd function, therefore that name. If x by y is on the graph of an odd function, then negative x by negative y is also on that graph. Therefore, if you can take this graph and turn it around 180 degrees, it's going to be symmetrical. So it's symmetrical, rotationally symmetrical around the origin. An even function is where f of negative x equals f of x. See, I like to say that it absorbs the negative sign. For example, x squared, or x to the fourth, or x to the sixth, or x to any even power. If x by y is on the graph of an even function, then negative x by y is also on the graph. So the graph is symmetrical by reflection through the y-axis. Left-right symmetrical. So these algebraic properties, odd or even, are related to these geometric properties: symmetrical around y-axis, symmetrical around the origin. This is not a property of functions. If this is clearly not a function, so I can't talk about this as a property of functions. Okay. Now here are what are called increasing or decreasing functions, though I prefer to call them order preserving and order reversing. An increasing function is one where if you increase the input, then you increase the output. It means the graph goes from lower left to upper right. A decreasing function is one where if you increase the input, then you decrease the output. Therefore, I call it order reversing. It goes from upper left to lower right. Here, if you have a graph like this, it'll be reversing or increasing and decreasing in different parts. For example, this graph is increasing from x from negative pi to negative pi halves, and from pi halves to pi. It's decreasing from negative pi halves to pi halves. So it's increasing, then it's decreasing, then it's increasing. Now, if something is increasing, then starts decreasing, then for a brief moment at the peak here, it's what's called a local maximum. It's the largest value in its neighborhood. So here, the point a by f of a, it's the biggest value of y equal to f of a is at x equals to a. Point where it decreases and pauses and increases, then for that brief moment there, it's a local minimum. It's the smallest value in its neighborhood. So that if you, no matter which way you go, left or right, you get a bigger value. And so we write this as minimum value of f of y equals f of a at x equals a. There's also global minimum and global maximum. A global minimum is the smallest value of f anywhere, like here. The global maximum is the largest value of f anywhere, like here. Here's a graph which starts near 0, goes to a global max, falls down, and rounds out at a local minimum, rises up and rounds out at a local maximum, falls down to a global minimum, and then goes back to 0. So we have some examples. Here's a graph. What is its symmetry? It's symmetric around the y-axis. This one is symmetrical around the origin. Although it's not a graph of a function, it's more of a general relation. What symmetry does the graph, has the graph of y equals absolute value of 2x? Well, if f of x equals absolute value of 2x, then f of negative x is absolute value of twice negative x. And the negative cancels out from because of the absolute value. So it's absolute value of 2x. These are equal. So f of negative x equals f of x, and that's an even function. It's symmetrical around the y-axis. Here we have the function or relation. Well, it is a function really. Xy equals 12. If we replace x by negative x and y by negative y, then you get the exact same equation. So so therefore it's symmetrical when you flip both sides, and that's symmetrical around the origin. Here a function negative 3x cubed plus 2x. Is it even, odd, or neither? Well, you try f of negative x, see what happens. You plug negative 3 negative x cubed plus twice negative x. The negative comes out of the x cubed because that's an odd function. Opposite of 2x is minus 2x. That's 3x squared minus x cubed minus 2x. You can pull out a negative, and that's negative f of x. So f of negative x equals negative f of x, and that is an odd function. In general, if you have a sum of odd functions, the result is odd. If you have a sum of even functions, the result of that is even. Here we have a function absolute value, x minus absolute value of x. Well, is it even, or is it odd, or is it neither? Well, okay, what you're going to do is you're going to look at f of negative x and compare it to negative f of x and f of x. F of negative x is, after a bit of work, minus x minus absolute value of x. Negative f of x is, after a bit of work, minus x plus absolute value of x. F of x equals x minus absolute value of x. As you can see, this f of minus x equals neither f of x nor minus f of x. So therefore, this function is neither even nor odd. That should be expected. This is an odd function. This is an even function. You combine the two, you wind up with something that's neither. Now here we have a general rule. If we have any function whatsoever, then let's define this new function e of x by f of x plus f of negative x, all that divided by 2. That is even. Well, the proof is simple. You take e of negative x, get f of negative x plus f of negative x all over 2. The negatives cancel. You get f of negative x plus f of x over 2. And that's the same thing as f of as e of x. Therefore, e is even. In the book, you're assigned one problem where instead of a plus, we have a minus here, f of x minus f of negative x all over 2. And they ask you to prove that it's odd. Here's one where I do request that you go through the steps. And it'll be a lot like this. Now here we have a function graph. Where is it increasing? Where is it decreasing? Find local max, local min, global max, and global min. It's increasing on all these values of x, where f is less than or equal to negative 4. And also all of these values of f, where f is between negative 0.5 and 3. And all of these values of x, where f is at least 5. So it's increasing on negative infinity to negative 4, negative 0.5 to 3, and 5 to infinity. It's decreasing when x is between these two values, negative 4 and negative 0.5. And it's decreasing on this interval where x is between 3 and 5. Negative 4 to negative 0.5 and 3 to 3 by 5. The local minimum is this point here. Y equals a local minimum, excuse me. This point here, y equals negative 1 at x equals 5. Local maximum is here where y equals 1 at x equals 3. And by the way, when I'm asking for local min and max, I do want the value y and the x where that happens. It's not enough to just give one of those. The global minimum is here, y equals negative 3 at x equals negative 0.5. The global max is here, y equals 4 at x equals negative 4. Well, I do believe we're done here.